Clay minerals are hydrous aluminium phyllosilicates, sometimes with variable amounts of iron, magnesium, alkali metals, alkaline earths, and other cations found on or near some planetary surfaces. Clay minerals form in the presence of water and have been important to life, and many theories of abiogenesis involve them. They have been useful to humans since ancient times in agriculture and manufacturing. Properties: clays form flat hexagonal sheets similar to the micas. Clay minerals are common weathering products in low-temperature hydrothermal alteration products. Clay minerals are very common in fine-grained sedimentary rocks such as shale, mudstone, and siltstone, and in fine-grained metamorphic slate and phyllite. Clay minerals are usually ultra-fine-grained and so may require special analytical techniques for their identification study. These include X-ray diffraction, electron diffraction methods, various spectroscopic methods such as paragraph Bauer spectroscopy, infrared spectroscopy, Raman spectroscopy, and SEMEDS or automated mineralogy solutions. These methods can be augmented by polarized light microscopy, a traditional technique establishing fundamental occurrences or petrologic relationships. Occurrence: given the requirement of water, clay minerals are relatively rare in the Solar System, though occur extensively on Earth where water has interacted with other minerals and organic matter. Clay minerals have been detected at several locations on Mars including Ecos and MAW at Th Vallis and the Memnonia Quadrangle and the Elysium Quadrangle. Spectrography has confirmed their presence on Ceres and Europa. Classification: clay minerals can be classified as 1-1 or 2-1. This originates from the fact that they are fundamentally built of tetrahedral silicate sheets and octahedral hydroxide sheets, as described in the structure section below. A 1-1 clay would consist of one tetrahedral sheet and one octahedral sheet, and examples would be kaolinite and serpentine. A 2-1 clay consists of an octahedral sheet sandwiched between two tetrahedral sheets, and examples are talc, vermiculite and montmorillonite. Clay minerals include the following groups: kaolin group, which includes the minerals kaolinite, dict, halloysite, and nacrite 4. Some sources include the kaolinite serpentine group due to structural similarities. Smectite group, which includes dioctahedral smectites such as montmorillonite and nontrinite, and trioctahedral smectites, for example saponite. In 2013, analytical tests by the Curiosity rover found results consistent with the presence of smectite clay minerals on the planet Mars. Elite group, which includes the clay micas. Elite is the only common mineral. Chlorite group includes a wide variety of similar minerals with considerable chemical variation. Other 2-1 clay types exist such as sepiolite or attapulgite, clays with long water channels internal to their structure. Mixed layer clay variations exist for most of the above groups. Ordering is described as random or regular ordering, and is further described by the term Reichweite, which is German for range or reach. Literature articles will refer to a 1-ordered elite smectite, for example. This type would be ordered in an isis fashion. RO on the other hand describes random ordering, and other advanced ordering types are also found. Mixed layer clay minerals which are perfect A1 types often get their own names. A 1-ordered chlorite smectite is known as coransite, a 1-elite smectite is rectorite. History: knowledge of the nature of clay became better understood in the 1930s with advancements in X-ray diffraction technology necessary to analyze the molecular nature of clay particles. Standardization in terminology arose during this period as well, with special attention given to similar words that resulted in confusion such as sheet and plane. Structure: like all phyllosilicates, clay minerals are characterized by two-dimensional sheets of corner-sharing CO4 tetrahedra and or AlO4 octahedra. The sheet units have the chemical composition 3O4. Each silica tetrahedron shares 3 of its vertex oxygen atoms with other tetrahedra, forming a hexagonal array in 2 dimensions. The fourth vertex is not shared with another tetrahedron, and all of the tetrahedra point in the same direction. That is, all of the unshared vertices are on the same side of the sheet. In clays, the tetrahedral sheets are always bonded to octahedral sheets formed from small cations, such as aluminium or magnesium, and coordinated by 6 oxygen atoms. The unshared vertex from the tetrahedral sheet also forms part of one side of the octahedral sheet, but an additional oxygen atom is located above the gap in the tetrahedral sheet at the center of the 6th tetrahedral. This oxygen atom is bonded to a hydrogen atom forming an OH group in the clay structure. Clays can be categorized depending on the way that tetrahedral and octahedral sheets are packaged into layers. If there is only one tetrahedral and one octahedral group in each layer, the clay is known as a 1-1 clay. The alternative, known as a 2-1 clay, has 2 tetrahedral sheets with the unshared vertex of each sheet pointing towards each other and forming each side of the octahedral sheet. Bonding between the tetrahedral and octahedral sheets requires that the tetrahedral sheet becomes corrugated or twisted, causing detrigonal distortion to the hexagonal array, and the octahedral sheet is flattened. This minimizes the overall bond valence distortions of the crystallite. Depending on the composition of the tetrahedral and octahedral sheets, the layer will have no charge, or will have a net negative charge. If the layers are charged, this charge is balanced by interlayer cations such as Na+ or K+. In each case, the interlayer can also contain water. The crystal structure is formed from a stack of layers interspaced with the interlayers. See also, clay, expansive clay, mudstone clays on planet Mars, Ailis quadrangle, composition of Mars, timeline of Mars Science Laboratory. The Clay Mineral Society, references, http, www.claysorgarchive 1-1-19 PDF, Clays on Mars, more plentiful than expected. Science Daily. December 20, 2012, A.S. Ravina, E. L. Volkordsen, B. E. Clark. The Surface Composition of Ceres, Discovery of Carbonates and Iron-Rich Clays, http, www.nasa.gov News Europa Clay-like Minerals 201312111 HTML, ABCD Amethyst Galleries. The Clay Mineral Group. February 22, 2006, 2007, Agel, D.C. Brown, Dwayne. NASA rover finds conditions once suited for ancient life on Mars. NASA. Retrieved March 12, 2013. War, Mike. Mars could once have supported life, what you need to know. Space.com. Retrieved March 12, 2013. Chang, Kenneth. Mars could once have supported life, NASA says. New York Times. Retrieved March 12, 2013. Moore, D. and R. C. Reynolds, J.R., 1997, X-ray diffraction and the identification and analysis of clay minerals, 2nd ed. Oxford University Press, New York, ABC Bailey, S.W., 1980, Summary of Recommendations of AIPEA Nomenclature Committee on Clay Minerals, American Mineralogist Volume 65, pages 1-7. 1.